Most of what I'm going to be Oh, thank you. Most of what I'm going to be covering doesn't require 6 months of engineering efforts or learning the Postgres source code, maybe the documentation a little bit, maybe. Yeah, that's sort of like the intent behind this talk. And yeah, in a nutshell, I'm planning on covering on topics like toast, vacuum, indexes, partitioning, some different kind of deployment patterns, and if there's time, maybe some logical replication things. But ideally, like it's all Postgres native concepts, stuff that you can basically find in documentations. My name is Shayon. I'm based out of the Boston area, and I'm an engineer at Tines. Tines is an intelligent workflow automation platform used by security and IT teams. What that means in practice is that we run workflows on behalf of our customers at a scale of about a billion action runs a week. It's all backed by Postgres. It's at the heart of it. And that's all I'm going to be saying about Tines today. I'm not here to sell you Tines. However, I'm here to share patterns and pitfalls that I've learned scaling Postgres in production. I've run Postgres in Aurora, RDS, cloud, and self-hosted deployments. So I'll try to cover things that sort of like more generally apply on to both worlds. Quick disclaimer before we get going. If you spend time in database discussions, like the answer to almost every question is it depends. And that's generally true here. Everything I'm going to be sharing today has worked for us at times at our scale and with the trade-off that we are comfortable with with our workloads. Your tables are different, your queries are different, your 3 AM pages are different. So please take everything as an input, not gospel. Benchmark things in your own environment before you adopt them. And I hope by the end of this talk, you do find something interesting. And yeah, so before we get into any specific optimization or feature, I want you to spend a quick minute on something foundational. And honestly, this is kind of the major theme of the talk as well, is you'll notice that we're going to spend a lot of time talking about how you think about your data, then tweaking Postgres' default parameters. And that's intentional because every decision you make about indexes, partitioning, vacuum tuning, your scaling strategy, all of it depends on the understanding of how your data is actually accessed. What's the read to write ratio? What tables are
So I
hot?
see that there was a lack of clarity.
I'll
You
just
weren't
unmute
supposed to
that.
investigate this code base. You were supposed to.
Oh, thank you. Sorry, I wasn't sure if it was like lack of clarity on the slide or not, but yeah, let me know if there's any glitches with the slides. Um, so yeah, your read to write ratio, your data being accessed and stuff like that. So um, yeah, like if you skip the step and sort of like jump straight to solutions, there's a lot of guessing, and guessing at scale can be expensive. So jumping straight in, this is, I'm sure, like if you run Postgres at a decent scale, a lot of this should be familiar to you. The PG user stats tables tells you a lot about your table, like sequential scans versus index scans, your how many reads, writes, deletes you're doing. Um, and one thing is very interesting here is like the dead number of rows. And we'll talk about vacuuming towards the later of the talk as well. I know it's everybody's favorite topic. And if you have enabled PG stat statements, which I'm sure, again, most of you likely have, um, you also get query level statistics. I think like this is a great place to start. A lot of vendors these days offer these sort of like visualizations about your application in general. Once you have this picture, I feel like everything else like indexing, partitioning, schema changes start becoming an informed decision basically. So think about a table that stores execution results. You'll see that I'll be talking about jobs and events and execution results a lot because at the heart of like what Tines does and the kind of data that Tines works with is around this general stream of stuff. So like imagine like the recent stuff, like recent events or recent jobs, like things that have happened in the last few hours is being quoted constantly. You're showing that in a dashboard somewhere. Your workers are writing to it. Your users are pulling that from APIs or something like that. But the same table also has 6 years of old data sitting right next to it. And Postgres has no idea which rows are hot, which are cold. It's maintaining indexes over all of it, running vacuum over all of it. Your buffer cache is filling up with old pages that nobody is looking at. Your hot queries end up being like competing with cold data for I/O, CPU, memory. And partitioning is a good thing to consider here, and we'll talk about that as well. But there's something simple here as well. It's like archiving old data to a separate table or pushing it to an external storage. But you cannot make that call until you actually measure what's hot and what's not. And PG stat user tables query from the previous slide is where typically you would want to start. Now that you understand the data and or like how your data is accessed, it would be good to understand like what Postgres does behind the scenes that I think a lot of people don't really think about until it kind of bites them, right? Like, let's say if you're storing a JSON-B payload, large text fields, or anything beyond 2 kilobytes per column, Postgres is silently doing something pretty clever that can sometimes have a real impact on performance. Toast, as it stands for the oversized attribute storage technique. I've used the acronym way often than the actual full name, but Postgres stores everything in 8 kilobyte pages, and there's a column value when it exceeds like 2 kilobytes. Postgres compresses it, and if it's still too big, it slices it into chunks, moves it into a separate hidden toast table. It doesn't really show up in your schema, and your main table maintains a pointer to it. However, there's a little bit of performance cost there. Like every time you access a toasted column, Postgres follows the pointer, reads the chunk from the disk, decompresses it, reassembles it, and then gives it back to you. Postgres has a few toast strategies like extended that is default for JSON-B and text. It compresses it first and then moves it out of line. External skips compression, which is useful for raw bytes. And main tries to keep things in line and only moving it out if it has to. But what do you do with this, right? Like the first thing is to, I quite often see is the toast or data being part of the metadata that you're storing and then being part of the same table, right? So like a simple query like select star on a table with these big columns can end up basically pulling your metadata, even though which you most likely need, along with 50 kilobytes or 2 kilobytes or 2 megabytes of JSON blob, and you're paying the entire decompression cost of having Postgres read it from the disk, deassemble it, and then return it back on the wire to the client again. A very simple thing to do here is just auditing your queries. ORMs are kind of notorious here, where like they like to do like select star on your tables, and you don't even know about how much data you're pulling back and forth from your server. The second thing to consider is whether this heavy payload even belongs in the same table, right? Like if you have a table that stores this metadata and the full JSON-B, like could this JSON-B live in a separate table? And every time you need it, you basically do a join on this. And this kind of stuff also allows you to control the toast strategy per column if it needs to be in the same table, which is something I think some people don't realize, but the documentation is really good at this and covering a lot of these things. And definitely keep an eye on toast size. My coworker, Julianne, recently published a very good article on our engineering blog where we talk about a 17 terabyte table and partitioning it. And a lot of that had to do with like toast and vacuuming, stuff like that. And I've seen firsthand how big toast table sizes can get. Now, there's one fundamental thing about Postgres that is the way it handles updates is fundamentally different from other databases like MySQL or similar. So understanding this core concept can also explain a lot about performance and disk usage and also vacuum itself. If you've used MySQL, you might be familiar with InnoDB, where like it modifies rows in place and keeps old version in an undo log. Postgres works completely differently. When you update a row, Postgres writes a brand new copy with the updated values and marks the old version as expired by setting its Xmax. So both versions live in the same heap, and that's the core of MVCC. It's what let readers and writers not block on each other, basically. So the cost is you're constantly creating dead tuples. And if you have a table with 5 indexes and you update an index column, Postgres writes the new heap tuple, marks the old one dead, adds a new entry, and you have like all these like 5, 6 indexes and 5, 6 operations going on, and all of this is getting logged to wall. There's a nice optimization here, HOT or heap only tuples. If the column you're updating isn't part of any index, there's room on and if there's room on the same page, Postgres skips all the index updates entirely. It writes the new tuple on the same page and it chains to the old one, turning all these 6 writes into one, basically. There's some limitations here under certain conditions where if you're updating an index column or the page is full, you're back to the full write amplification. So it helps to be thoughtful about which columns you index and leaving some fill factor, which is the HOT concept, headroom on heavily updated tables, which makes a pretty big difference. Now, given you know about like MVCC and how it can create dead tuples on every update, a really powerful pattern can be to ask yourself, do my writes actually need to be updates or can they be inserts instead? right? So like take a table that tracks a bunch of status of jobs or events. The traditional approach is that you insert a row, and then every time this job completes, you can mark its progress from pending ad to running to completed ad and that kind of stuff. Each of these updates can create a lot of data tuples. If you're doing millions and billions of jobs a day, that's how many data tuples you're accumulating, which triggers vacuum, which triggers more resource usage and stuff like that. The alternative can be to have a table that acts as an append-only event log. So instead of updating the status, you're basically inserting a new row for every state change. Now, this way you avoid the dead tuples and vacuum barely kicks in, and your indexes basically stay compact and don't get invalidated. I think there are a few obvious questions here. Like one is if you're only inserting, how do you get the current state of something? You can use select distinct on to grab the latest event per entry, which works fine for individual lookups. But if you're doing it at scale, you probably want to look at like materialized views where you have a pre-computed latest state that scans this table. And instead of like querying an entire table or index scan, you basically look into or directly query the materialized view, which you can refresh every five minutes. The other thing I think people worry about with append-only growth is with append-only is growth, which I think is a fair concern. Because every state change is now a new row. So the table grows faster than an update in place. But this is where I think partitioning by time range can really shine if you're able to use it, where you're inserting these rows and as like older events accumulate, you're moving those into like range-based partitioning. And depending on the data lifecycle requirements of your app or of your product, you can basically drop those old partitions eventually, keeping the more recent data fresh on the more recent partitions. So when your query hits those partitions, it has as little tables to scan as possible, basically. And combine this with the right indexes. This pattern scales quite well for especially write-heavy workloads, in my experience. Now, we've talked about like writes in Postgres, so let's talk a little bit about reads. Indexes are probably the first thing that people reach for when queries are slow. And that's not wrong. I think a good index can turn a sequential scan into a microsecond lookup almost. But there's a gap between sometimes I think that adding an index and adding the right index. So maybe let's take a quick second to take a look at B-tree. I think B-tree indexes are great. It's really hard to beat a performance of a B-tree index, right? Like it's ideally a balanced tree where the leaf nodes contain the index values along with the tuple IDs that point back to the heap rows. Now, with MVCC, when a row is updated, the old index sticks around until a vacuum cleans it up. But even after a vacuum runs, it only marks the space as reusable. It doesn't actually compact the index or return pages back to the operating system. So over time, especially on tables with a lot of updates or deletes, a lot of churn, the index can end up being much larger than it needs to be. And I've seen indexes where the actual data is 3, 4 times larger than the actual size of the data. Which means like every index scan it's going through a lot of pages, resulting in a lot of I/O and stuff like that. And there are a few things you can do to catch this, and this is typically what most people talk about index bloat. There are queries that from the Postgres metadata catalog tables that you can query to understand how big your indexes are getting and keeping a track of those basically. However, one thing I want to call out is as your application or product grows or matures, um, you may find that indexes that were added 5 years ago no longer serve a purpose because the query patterns would have changed. So it's good to question your indexes over time and see if you actually need those indexes or not. The other is reindex concurrently, which is, I think, recent as of Postgres 12. And it's quite nice. The concept is very simple. It creates a brand new index, swaps it in for the current one, and then drops the old index back. And it helps avoid a lot of this bloat as well. It's nice to be on top of this if you can run it periodically, because if compared to, for example, like like if you see your queries getting slow or when you see like a large IO bill from your cloud vendor, these kind of operations can sort of like do basic housekeeping behind the scenes. Partial indexes are one of my favorite features, and I feel like it's still pretty underused and for like a very beautifully simple idea. which is say you have a status column and 90% of your rows are in a terminal state, like completed, and you only query or you only care about like pending ones for the most amount of time, which means that you don't really need to be indexing 500 million rows. You can add a partial index with a where clause with then with the appropriate index definition, and Postgres will only include those match rows for that condition. So instead of a 500 million row index, you end up with like 10, 20, 30 million row index, basically. It's smaller, faster, fits entirely in memory. And Postgres has to maintain it only when the row actually matches the condition, which is also a win-win, I feel like. Function-based indexes are also really nice. I think I saw something about this at Postgres Weekly or something a few weeks ago, but the idea is very simple here again, where like you can use functions with like where lower of an email equals something, you can add an index for it. And it works similarly too. Like Postgres will be able to choose that index or prioritize that index for a query pattern that you're doing very repeatedly and kind of go from there. Um, but I think the call out here would be that it has to be a literal match. So if you're doing something like a lower of an email or like a some other function call, it won't be able to use that index. So it helps to uh, put an index, or if you see your query where like collectively it's running an average of like 400, 500 milliseconds, and you're doing that millions or billions of times a day. Stuff like this like can speed things up and while keeping your index footprint quite minimal. Hash indexes are also something that I wanted to call out because sometimes in your application there are a lot of workloads where you may see that it's doing purely equality checks, and B-tree indexes are great for that. Hash indexes are kind of like the perfect fit for those kind of things where it is it can be 20-30% smaller than B-tree indexes. Um, they're also covering indexes with include, where it can really significantly help reduce IO. And I think they're a little bit underused as well. For example, so you frequently look up like statuses of some unit by tenant. And you also need to get the created ad and updated ad or some other column alongside it. Normally, Postgres would use the index to find the matching row and then go back to the heap to fetch those extra columns. But with include, those columns are also stored right next to the index leaf. So Postgres doesn't have to visit the heap at all. It can satisfy this entire query from a single index lookup. We have found that like for high throughput queries, this could cut your IO quite significantly as well because there's just less round trip work happening. Gin is another one. I think if you have like worked with like JSONB in Postgres, generalized inverted indexes, you might be familiar with this. It's basically Postgres breaking the JSON structure to a key value pair and then indexing each one separately. So if you're using a containment operator, Postgres can go directly to the inverted index and give you back the result. I found that this works quite well. I've also found that like a pattern that can emerge because JSONB something is like you don't know the shape of your data and you're like putting in a database and almost like the entire JSONB feels like it's like all the keys inside the JSONB is important. But sometimes you would notice that the if you were to like create like a histogram or something of your data fetch pattern, you'll notice that some keys are being requested more often than the others, right? So there's an opportunity there to consider generated columns or like turning that into a first class table and then putting a B-tree index on it because then it's much faster than the GIN index. And I feel like that also keeps your data model quite honest because now you don't really treat the JSON-B as like everything is equally important. So kind of like questioning is everything inside your JSON-B column is kind of like serving its purpose or not is useful. I know I've been talking for a while, so a little mean to get everybody's attention back. Now,
Sorry, do you mind just going back a little bit to the last slide? I always
sure.
get confused between the double arrows and the at operator and the single arrow. Just curious, how do you think about like when to use those?
That's a great question. Honestly, I think I've only used the containment for the most part of the time because I've found that that is always resulted in good GIN index lookups. Um, Yeah, I think the ad refers to like the each individual segment that the filter should work against, versus like if you're just like looking for keys, like like you have a JSON nested hash and just like give me this key, then it will work. Um, but I know there's like a lot of different ways that you can actually do like almost JSON path based stuff with JSONB, but I actually haven't used a lot of the other operators outside of the containment, quite frankly.
So that you use that kind of like as an includes check rather than like
Basically, yeah.
trying to match specific values.
Yeah.
Got it.
And then like trigger the gin index because like it kind of like knows like exactly which part that you're looking at. Cool. Yeah, and absolutely feel free to interrupt if anybody else has questions and stuff. But yeah, maybe we can chat a little bit about locks. I wanted to give locks a positive spin. A lot of the times when I get into an incident, I feel like it has something to do with a lock. But I found that skip lock is something that sits at the core of like how Times does durable job orchestration, and a big part of like our fair orchestration and queuing is lives on Postgres. The skip lock is at the center of it. The idea is very simple here, where like you want multiple workers to pull jobs from a table, and you don't want other workers stepping on each other. So without skip lock, if two workers were to grab the same row, one of them blocks waiting for the other to finish. So with skip lock, you sort of like make sure that there's less lock contention, and it basically turns Postgres into a pretty capable job queue. Um, you also get transactionality here, right? So if something were to roll back, you get a clean state back. You get to commit everything atomically, and it works really good. Like at a pretty decent scale, like we've done like 10,000 jobs per minute, and it's pretty good. But there are also like alternatives like Redis and SQS infrastructure, which also have like other pros. But in my experience, like Skiplock works really well. Skiplock combined with a partial index, combined with like some status equality checks, and your Postgres instances can go really far. Um, the other is advisory locks. I think this is like fairly very widely known at this point, but I still wanted to give advisory locks a shout out because it's a great way to coordinate access in a distributed system using like a very nice application level locking primitive that comes straight out of Postgres. And unlike row logs, they don't block. They don't actually lock any rows or tables. They're purely logical. Um, and these examples show like a really common pattern where like if multiple workers are, let's say, are trying to process a customer charge and you want to make sure only one worker can work on them, advisory locks work very nicely here. The trilog variant is also quite nice because if you don't want the lock to wait and return fast, it works really nicely because you can like do the fast fail method there as well. And all of this is visible, like you get the deadlock detection, you get visibility in PG locks table, and they get cleaned up after the session disconnects. So it all feels like proper first class citizen to me. Um, Shifting gears a little bit, maybe we can discuss a few different ways of you can deploy your Postgres instance, especially to sort of like how we sort of have gone around scaling some of the write, but also like read workloads. Um, this is a very standard architecture. I feel like if you're a production app today, you probably want to start here, like have one primary, one reader at least, so that you can get high availability. It's not nice to have it's table stakes for the most, like if like if you have customers and relying on your business and stuff like that. Readers are also nice. You can like add as many readers as you want. You can group your readers. You can do your reporting queries against a bunch of group readers. You can do analytics, dashboard, search, and a bunch of other stuff. PG Bouncer in front of these is a really good idea. Postgres forks a process for every connection, so the memory overhead adds up over time. PG Bouncer is very good at like multiplexing thousands of application connections through a small pool of actual database connections. Outside of memory reason, it's also really good for operational tasks. I think Arca gave a really nice talk on using PG Bouncer for zero downtime upgrades, which I recommend checking out. I promise Arca did not ask me to give that shout out. Um, and before you like think about splitting or going to multiple clusters, which I'll talk about in a little bit, um, partitioning is also a way to sort of like split a single table into smaller physical pieces. And the most common pattern is range partitioning by time, like I was talking a little bit earlier. I think the huge benefit here is the data lifecycle. Like you use something like pgpartman, and you get like tables created for you based on your partitioning key, and over time, like your older partitions get dropped, so you don't have to run delete on millions of rows. You don't have to worry about vacuums or IO pressure and that kind of stuff. And that gets you pretty far as well. Partition pruning, I mean, there's a lot I can talk about partitions and partition pruning and stuff like that. But one thing I wanted to call out is that, especially as your application matures and your query patterns change, it's really important to make sure that your access patterns really align with your partitioning strategy. I've seen cases where like the query would not have like the partition key, and Postgres ends up scanning all the partitions, which then ends up being like quite expensive and not so productive. Um, Another constraint it's also very easy to overlook, is that your primary key and any unique indexes to you have should include the partitioning key, because Postgres can only enforce uniqueness within a single partition. This caught us a little by surprise when we were exploring some partitioning work, so figured would do a quick shout out on that. This is something we do today at times, and the general idea is that a single set of CPUs and memory and networking bandwidth can only go so far. And right before we actually explored like logical sharding, where like sharding a table by multiple pieces, we are doing something like this, where like if you're doing like business in B2B or enterprise or some similar, you may have customers that can request isolation. It could be for your own reasons, performance, to give better performance guarantees, but it could also be for compliance and other things. So the stack per customer model is really clean because your application code doesn't change. It sort of like forces you to have the same schema and you're running the same app, and maybe even the same deployment pipeline, depending on how you deploy this. But the idea is that you just spin up a new stack for new customer or even a group of customers, which we call like a multi-tenant stack. And you can pack multiple customers in the same cluster, sharing the same writer with a bunch of readers, or you give a dedicated customer, dedicated writer and a bunch of readers. And this works nicely because like now some of the expensive queries get a more breathing room in terms of like system resources. The blast radius is naturally isolated. If a customer query gets really bad, it doesn't peg the CPU and result into a bunch of other noisy neighbor issues. And everything that we talked about, like partitioning, connection pooling, vacuum tuning, everything you can consistently apply across these stacks as well. And from a data modeling point of view, I mean. That said, there's a trade-off here. And the trade-off is operational overhead. You're now managing many clusters instead of one. So like I think like there's some sort of like conscious choice needs to kick in here, right? Like at times like we have like 100 plus clusters across 4 regions, and we have decent operational maturity to run this at scale, even though there's some room for more improvements and stuff like that. So yeah, your mileage may vary, but this is one way to sort of like help scale your writes, for example. The other is logical sharding. You know, there's Citus and there's pgdog today. Citus has been around for a while. That lets you declare like distributor tables that transparently shard across worker nodes. And pgdog is a little bit more new and is open source proxy, also like a drop-in replacement for PG bouncers. I think there are trade-offs to both of these approaches. For example, cross-shard queries can get a little bit complicated. Or like, but then there's also operational complexity for managing something else earlier. But yeah, if you generally need more write throughput or from what a single writer can handle, these kind of like sharding techniques can also help. It kind of like really depends on your comfort level on like the trade-offs involved here. Um, I know we're almost over time, so I'll skip through some of these very quickly. Lock timeouts. If you don't have lock timeouts, go and put lock timeouts. There are a lot of uh, like most DDLs in Postgres are fine, but once in a while you'll come across some ultra statement that ends up in a lock queue, and a log timeout is really saves the day there, basically. There are a lot of like libraries these days that can sort of like lint your code when you're introducing schema changes that also go a long way. And time for a quick spicy take. Foreign keys. I love foreign keys. I'm not here to tell you they're bad. They're great for data integrity, but I think some teams could revisit foreign keys and see if they're still useful in your application. Because foreign keys can compound, like there can be like costs that can compound over time. Performance on insert updates and deletes is one. Lock contention is another one when you update or delete a reference row. But these are also like the features of why you would want to use foreign keys in the first place. And also the requirement of an additional index with foreign keys. So at times, at least, we do both. We use foreign keys for places where it matters, but on very active hot code paths, we do not use foreign keys today. We have jobs that help us ensure data integrity, but we found that without foreign keys, we can actually like make a lot of these hard code paths be very um fast and performative. So again, your mileage may vary, but if one thing I would like you for you to take away from this slide is question your foreign keys, see if they're pulling their weight. If not, they could be a safe candidate to drop. And if they are pulling their weight, that's great. Counting is also a bit of a slow operation in Postgres. I don't think that's like my gripe with Postgres because in general, counting is a hard problem. It's a hard distributed problem. But one thing that kind of the MVCC design hurts a little bit is that because Postgres can store simple row count because different transactions see different sets of rows depending on the snapshot. Every count has to go through the index or the table, and that can get expensive. PG class rel tuples is your friend if you can get away with approximations. It's only as approximate as your last analyzed time. Two things that I found very useful for exact counts is a counter cache pattern, where you maintain a count in a separate table that gets incremented on every insert and decremented on every delete. But if you have lots of concurrent writes hitting the same counter, that same row again becomes a bottleneck. So the slotted counter pattern is quite nice, where you distribute your count across a few different slots. And every time you need to get a count of something, you query these different slots. It could be 4, 8, 16, 32, and sum it up, which would still be faster than counting going through all the rows across the index and or the table. I'll skip the logical replication and move straight to the questions bit, but I'm happy to cover that. Summing it all up, I think if there's anything I would like you to take away from this session is this: understand how your application uses the database, its read patterns, write patterns, how it updates and deletes, how fresh the data is, and things like MVCC, vacuums, locks, toes, wall indexing. These aren't like abstract internals to ignore. These are basically the fundamentals of the machinery that you're running on. So once you have a good understanding of these things, everything else sort of like starts to click. You'll know when partitioning makes sense. You'll know when a partial index makes sense. You'll recognize dangers like migrations before they hit production. And you don't need to re-architect everything or move off of PostgreSQL. You just need to understand the engine that you're running on and work with it. And yeah, that's how you scale Postgres without boiling the ocean.
Awesome. Thank you so much. I'm gonna stop the recording now.